Hi, in this video, we'll cover ions, ionic compounds, and ionic bonding, how to write the formula of ionic compounds, and how to name ionic compounds, which is what we covered in our first class session, or what we reviewed in our first class session last Thursday. Okay, let's start with the definition. An ion is an atom or group of atoms that has a net positive or negative charge. So the ion has a net charge, either negative or positive. The cation is the ion with a positive charge, and the cation is formed when a neutral atom loses one or more electrons. Now, remember that an atom has positive protons in the nucleus. Look at an atom. Right? There are positive protons in the nucleus, and there are negative electrons outside in the extranuclear space. A neutral atom has an equal number of electrons that are negatively charged and protons that are positively charged. So when an atom loses a negative electron, it now has more positive protons than electrons, and therefore it will end up with a positive charge. Okay, so if you look at the example shown here, this is the element sodium. A neutral atom of sodium has 11 positive protons in the nucleus and 11 negative electrons in the extranuclear space. If an atom of sodium loses one of those negatively charged electrons, then now it has then electrons, right? And you can see that there is now more positive protons than negative electrons, and then there will be a net charge. So the ion that forms now has a plus charge when the atom loses one electron. That is a cation. The anion is the ion that forms with a negative charge, and it forms when a neutral atom gains one or more electrons. Let's take a look at the example shown here. Chlorine, a neutral atom of chlorine, has 17 positive protons and 17 negative electrons. But when an atom of chlorine gains one electron, it now has an overall charge of -1, right? So there is a net negative charge. And then the ion that's formed is called chloride ion. Okay, you might be asking, why is the sodium losing and why is the chlorine gaining? And can the sodium gain and the sodium and the chlorine loses? Well, there are some, there's an explanation to why the sodium tends to lose and why the chlorine tends to gain. Let's look at the periodic table, and the periodic table will explain that to us. Okay, so the idea here is that atoms or elements would love to have a full valence shell, right? So all the elements here, they seek to have a full valence shell. All right, valence is the outermost shell. And shell is what we also call the energy level. So when you start learning about the structure of the atom in details in chapter 7, you'll see that the electrons in the extranuclear space are not randomly arranged, okay? They're organized in what we call energy levels or shells. So if you think about the nucleus in the center with the positive protons and the electrons being in the extranuclear space, these electrons are not randomly placed in that extranuclear space, but they are very organized in specific locations, probability with a high probability, right? So, you could see an electron in here, or electron in here, and an electron in there, and so on and so forth. Now, the outermost shell is what we call the valence shell, the very outermost shell, which is the one that is farthest from the nucleus. That's what we call the valence shell. Okay, so all atoms, they seek to have this full valence shell. Everybody wants to have a full valence shell. And let me tell you this, there is a group of elements in the periodic table that actually do have a full valence shell, and they are the most stable. We found these to be in group 8A, which is what we call the noble gases. That very last column or group is called group 8A, and these are the noble gases. And when we looked at the noble gases, we saw that the outermost shell, or their valence shell, is full with electrons, which gives them a unique stability. They're really very, very stable. They don't really want to gain or lose any electrons. They're not interested in forming bonds or compounds. They really participate in chemical reactions. I mean, the only time you could get them to do something is by harassing them in the laboratory. But other than that, they're kind of content and happy. And that stability is because of the full valence shell. Think about yourself when you have a nice, full meal and you're satisfied. So are the noble gases. And that's why, by the way, they call them noble. Right? They really don't want to do anything, and they don't do anything. They rarely ever do, form compounds or bonds with other atoms. So everybody else in the periodic table wants to be like these noble gases. Everyone else here wants to be like the noble gases. Of course, there are exceptions. What makes chemistry a challenging science is the exceptions that we see with all the rules. But the general trend that explains a lot of why the compounds that we see are formed is the desire, let's say, the desire of all of these guys and gals to have a full valence shell, right? Everybody wants to be like these noble gases. So that explains why, for example, the sodium tends to lose one electron, which we saw in the previous slide, and also explains why the chlorine likes to gain one electron. So let me tell you, sodium here, as you can see, in a neutral atom of sodium, there are 11 electrons. Okay, well, sodium loves to be like the noble gas neon that is closest to it in the periodic table. So if sodium loses this one electron, it's going to be just like neon with 10 electrons. It will have a full valence shell and it will achieve stability. We will also later learn about the octet rule, which is part of the full valence shell. All right, let's look at the chlorine. Chlorine right here. The chlorine has 17 electrons. Chlorine would like to gain one electron and have a full valence shell like argon, right? So chlorine loves to gain one. Let's take a look at another example. Let's take a look at calcium. All right, think about that. Calcium has 20 electrons. What do you think calcium would like to do in this case? Would calcium like to lose 2 electrons and have 18 electrons similar to argon? Or would it be easier for calcium to gain, 16 electrons and be like krypton? Well, as you might have answered, yes, it is easier for calcium to lose 2 electrons and be like argon. So what happens when calcium loses 2 electrons? Then it becomes a cation, which is an ion with a positive charge, and that is a +2. Remember that it loses 2 negative electrons, and now it has more positive protons, hence the positive charge. Okay, let's take a look at another example. Let's take a look at something like aluminum right here. Okay, what do you think aluminum would like to do? Let's see, aluminum has 13 electrons. The 2 noble gases that are closest to aluminum are the neon with 10 electrons and argon with 18 electrons. It's much easier for the aluminum to lose 3 electrons and have 10 and full valence shell like neon. So aluminum tends to form ion with a 3+ charge, cations with a 3+ charge. We see that oxygen with 8 electrons gains 2 electrons and have a full valence shell like neon, so oxygen tends to form ions with a -2 charge. Okay, so I'm going to go over to the next slide and show you a table which is in figure 2.11 in your textbook, and that table has all the ions I'm referencing to. Okay, so here's the table. You can see elements in group 1A, they all form ions with a +1 charge, with the exception of the hydrogen. Hydrogen is a nonmetal and it can lose or gain, but it does both really. Elements in group 2A, they all form ions with a +2 charge. And then we jump to elements in group 3A. Aluminum is the most reactive, really, element, or metal, I should say, in group 3A. So it forms an ion with a 3+ charge. Carbon sometimes forms an ion with a 4 negative charge, and most of the time, actually, carbon shares. Most of the time, carbon shares electrons. So you'll rarely ever see this species right here. Nitrogen and phosphorus, these are groups 5A. So group 5A forms ion with a -3 charge. Group 6A forms ion with a -2 charge. Group 7A forms ion with a -1 charge. And no, as we know, group 8A is the noble gas. So let me put the charges here. Group 1A is +1, group 2A is +2, group 3A is +3. I'm going to skip group 4A because carbon is, rarely ever forms an ion with a 4 negative charge. Most of the time it really shares. And then group 5A, -3, group 2A, 6A, -2, and group 7A is -1 ions. Okay. All right, so notice that I've only focused right now on groups 1A, 2A, 3A, all the way to 7A. And you might be wondering why I skipped the middle section right here, which has a lot of ions, as you can see. All right, so group 1A, 2A, 3A through 7A, those are called the main group elements. And these follow the octet rule that I described. They all want to be like the noble gases with full valence shell. Elements in the middle of the periodic table, which is 3B right here all the way to 2B in this section right here, these are called inner transition elements, and they don't follow the octet rule. The octet rule really applies to the main group element. But the inner transition element, which are in the center of the table, starting from group 3B to 2B, and some of that here, they don't follow the octet rule, and they tend to form their own ion. Unfortunately, there is no specific rule that would help you predict the charges on these elements, and you would have to memorize these charges. But the good news is you only have to memorize the ones that are shown in this table, and you don't have to memorize the charges that every single element in the periodic table forms. I was asked this question on Thursday, if you have to memorize the atomic number of every element or number of proton. Of course not. There is a periodic table in your book. There will also be a periodic table in the test electronically, and you see one on Alex, so you can always reference your periodic table at any time. There's no need to memorize the charges, but you do have to memorize the charges of these ions. Okay, so the inner transition elements that we can see here, those are the ones that are shown in the table. I'm going to take a look at a couple examples. Iron is a very popular one. We see iron a lot, and it is a reactive element. So it tends to form two types of ions, either an ion with a +2 charge or an ion with a +3 charge. Another popular one and a very reactive element as well is the copper. And it forms two types of ions, ion with a +1 and ion with a +2. Cadmium, only one ion with a +2 charge. Silver, only one ion with a +1 charge. Lead and tin are also reactive elements. Tin forms two different types of ions with a 2+ and a 4+ charge, and lead 2+ and 4+ charge. Now notice that all of these green blocks in the periodic table here are metals. And if you look closely, you'll see that all metals form cations, because all metals tend to lose electrons and want to lose electrons. So that's something that would help you, that all the charges on the metals are positive charges, right? All those green blocks are metals. And if you look at the nonmetals, all the nonmetals form anions. Okay, so let's now talk about how we name these ions. So when the element has a different name than the ion from which the element is formed. I'm going to go back to a couple of slides here and show you what I mean. So if you look at a neutral atom of sodium that has 11 protons and an 11 electrons, this atom is neutral, and we're just going to call it sodium atom. When the sodium loses one electron and it forms a cation, it is no longer called the sodium atom, it's called a sodium cation. And we have to make this distinction because the ion is a very different species than the atom from which it's formed. It has very different physical and chemical properties. The sodium element that is neutral is a solid, and it's very, very highly reactive. You mix that sodium, a piece of sodium with water, and you have an explosion. Sodium ions, right? These are part of the salt, table salt, sodium chloride. They're not reactive. They don't form explosions. They're not solid, or at least, they're not metal in a way, but they're ions. Okay, let's take a look at the other example at the bottom here, which is the chlorine. A neutral atom of chlorine has 17 protons and 17 electrons. The ion that forms from the chlorine atom is now called chloride. It's not called chlorine anymore. I changed the suffix right here from chlorine to chloride, right? And once again, chlorine, the element, is gas that is poisonous, but the ion chloride, again, it's part of the table salt, and it's not poisonous, and it's not a gas. Right, so you can see the physical properties and the chemical properties are completely different. It's like two different things, two different species, and therefore we have to name them differently so we can distinguish between them. So let's go over the naming of these ions. Let's start first by naming the ions and then see how the compound forms, and when the compound forms, how we name that. Okay, I'm going to go into the slide here and show you on a white screen, on a whiteboard, how to do that. Okay, so we're going to start by naming the cations first. Okay, we're going to first start naming by cations, and then we'll name the anions. And I'm going to start with the simple ones, the ones in the main group elements. So remember, the main group elements are the elements in group 1A through 7A, 1A, 2A, all the way to 7A. These are the main group elements, on the sides of the periodic table. All right, cations, the naming is quite simple of these specific cations. All we have to do, just like what I did with the sodium, is add the word ion next to it. So the sodium ion is just called sodium ion. So you see, I just put the word ion next to the name of the element. Calcium ion, right? We could see potassium, that's in group 1A, so it forms an ion with a +1 charge. I'm going to call it potassium ion. What about aluminum? We just saw that aluminum is in group 3A, which means it forms an ion with a +3 charge, so it's called aluminum ion, and so on. Okay, so it's pretty straightforward with cations. With anions, what I did with the chlorine/chloride is how we name anions in the main group elements. And basically what we do is we're going to use the suffix "ide." Okay, so the element chlorine is in group 7A. It gains 1 electron and it forms the chloride. So chlorine becomes chloride. All right, bromine becomes bromide. Both of these are in group 7A. If you look at something like the oxygen, which is in group 6A, we've just seen that oxygen forms an ion with a -2 charge. So it becomes, instead of oxygen, it is now called an oxide. Sulfur is sulfide, right? So the suffix is "ide." One more example, let's take a look at the nitrogen. Nitrogen is in group 5A in the table, which means it forms an ion with a -3 charge, and we're going to call it nitride, ide, right? I know I'm a little fast, but if you have the table right next to you, when you kind of become familiar with where all the elements, the main group elements, are in the periodic table, you'll quickly realize, or you quickly determine what charge is on the ion. Okay, those are the main group elements. Okay, let's take a look at how we're going to name the inner transition elements. Notice that the inner transition elements, those are in the center of the periodic table. They're all metals and they all form cations, but we can't really predict by their position in the periodic table, what type or what the charge on the ion is, you have to memorize those. How do we name them? Well, there are two different ways we name inner transition ions that forms from the inner transition elements. There is a systematic naming, and there is a common naming. All right, and what I'm doing right now is I am naming the ions formed from inner transition elements. Remember that inner transition elements, they form cations. Okay, let's take a look at an example and we'll see the difference between the systematic naming and the common naming. All right, so let's take a look at the iron. The iron is a reactive metal, and it forms two different types of ions, either an ion with a +2 charge or an ion with a +3 charge, either a cation with a +2 or a cation with a +3. All right, the systematic naming of these ions is going to be as follows. So you're going to put the name of the element followed by the charge in parentheses, but we're going to put the charge as a Roman numeral and then the word ion. Okay, so this will be iron, that's the name of the element, followed by the value or the magnitude of the charge in parentheses. So I'm going to open a parentheses, and the charge here is 2. We're going to put that as a Roman numeral, and then the word ion. Whenever we name a cation, we've got to use the word ion, right? Like we did with the sodium ion or the calcium ion. We're going to do the same thing with these cations. Okay, with the Fe3+, we're going to call that iron. And again, the charge is 3+. So I'm going to put the magnitude of the charge as a Roman numeral in parentheses, 3, and then the word ion. So you have the iron 2 ion and the iron 3 ion. Let's take a look at a couple other examples. Let's do copper. We know that copper forms two different ions, either +1 or +2. So again, I'm going to put the name of the element, which is copper, followed by the charge as a Roman numeral in parentheses, copper 1, and then ion. This would be copper 2 ion, and so on. Okay, how about something like the silver? Well, if we look, we'll see that the silver forms only one type of ion. It's only a +1. There's no other ion that the silver forms. And because of that, I do not need to indicate the charge at all in the name, and we're just going to call it silver ion. Okay, so if the transition element forms, or if the transition metal forms only one kind of ion, then you do not need to indicate the magnitude of the charge in parentheses, because there's only one ion, there's only one type of ion, so there is no need to, put all of that in. Okay, what about the common naming? The common naming is very different. So the common naming originated long time ago from the Latin name and of the element, right? And what they did is they used suffixes. And we are using these common names today, and that's why you have to learn them. We actually use them a lot, and not just in textbooks, but also in literature, in a primary literature and in journals and all of that. Okay, so how do we name these elements according to the common name? The common name uses suffixes, like I said. So the suffixes are OUS for the higher charge, for the lower charge, for the lower charge, whatever the lower charge is, and IC for the higher charge. Okay, so it doesn't really matter here if it's a +2 or +3. It's a lot of people or a lot of students get confused or ask this question. Okay, is the OUS for the +2? Well, not necessarily. It's for the lowest of the two charges that form. So, for example, with the iron, right, the one with the +2, that's the one with the lowest charge, then that will take the suffix OUS, and the one with the +3 will take the suffix IC. And what we do is that we're going to use the Latin name and then of the element as a prefix, right? And then the suffix will be one of these two. So the iron 2 ion is going to be called ferrous ion, And the iron 3 ion is called ferric ion. Okay, let's take a look at the other two examples, copper 1 plus and copper 1 ion and copper 2 ion. Copper 1 ion is going to be called cuprous ion, and the copper 2 is cupric ion. All right, what about the silver? Since there is only one ion that forms from the silver, then it doesn't get any suffix. It's actually, it's just only one name for that, which is the silver ion. Okay, so this is the naming of the different ions, whether it's cations and also the anions. Okay, what we are going to do now is go over the ionic bond and how we name ionic compounds. Okay, what is the ionic bond? Now we learned about ions. So when ions are formed, right, there's an electrostatic attraction that occurs between these ions. This electrostatic attraction is what we call a bond. The two ions are next to each other, they're attracted to each other, they're bonded to each other, right? So the ionic bond, the nature of the ionic bond is really truly just an electrostatic attraction between opposite charges, right? So let's take a look at an example here, all right? If I take a look at the sodium and the chlorine, the most common example ever, whenever we discuss ionic bond, we always start with that example. It's pretty easy and simple, right? When the element sodium, we know that sodium loves to lose one electron, and we know that the chlorine loves to gain one electron. So this is the perfect, right, setup right here. So the sodium is going to lose that one electron, and it's going to give it happily to the chlorine, when the chlorine will also very gladly accept it. Once the sodium loses that electron, it becomes an ion with a +1 charge. Once the chlorine gains that electron, it becomes an ion with a -1 charge. Now you have oppositely charged ions. Once that happens, once that transfer of the electron happens, you now have an electrostatic attraction that is created between these two to form a compound that we call sodium chloride. Okay, so that is the nature of the ionic bond. It's just simply an electrostatic attraction between opposite ions, and this is because it started because of the transfer of electrons. So one of the key words with ionic bond is that word transfer. When one or more electron is transferred, right, from one atom to the other, you have created ions, you've created oppositely charged species, and then this electrostatic attraction is the ionic bond. Now, this is pretty cool, right? Now, think about that. Who loses the electron and who gains the electron? Always, in all cases, whenever an ionic bond forms, the metal loses the electron and the non-metal gains the electron. And that's why an ionic bond is always formed between metal and non-metal. There's got to be a transfer, right? And the only gals who are willing to give up electrons or lose electrons are metals, right? So ionic bond is always formed between metal and non-metal. The metal loses the electrons, the non-metal gains the electrons, and then the ions are formed, and then the ionic bond is created. Okay, this is a pretty simple example. Let's take another example. Before I move on to another example, let's name this. I know that you already know that, but see how we applied the names here. When we name an ionic compound, we start by naming the cation first and then followed by the anion. So we're going to name that sodium chloride. And we just learned that, right, that the anion chloride has the suffix "ide." Okay. Let's take a look at another example, another simple example. Okay, let's take a look at the bond that forms between potassium. We know that potassium is a metal, and bromine. Okay, and bromine is a nonmetal. Let's take a look at the table. Potassium is in group 1A, so we know that potassium likes to lose one electron. It's going to form an ion with a +1 charge. Bromine is an element in group 7A. Again, it's a halogen. It loves to gain one electron, and when it does that, it's perfect. It's going to take that electron from the bromine, right? From the potassium, sorry. And it will form an ion with a -1 charge. So once that transfer happens from the potassium to the chlorine to the bromine, you now have these ions, and the ionic compound that's formed is KBr, which we name as potassium bromide. Okay, so that's again another simple example. Let's take a look at a different one. How about the bond that forms between the metal calcium and chlorine? You've got calcium, metal, and chlorine, nonmetal, and these two guys approach each other, and we know now metal and nonmetal, that will form an ionic bond. Let's see how that works. Okay, well, calcium is in group 2A, and we know that calcium in group 2A would love to lose 2 electrons. It really needs to lose 2 electrons to form an ion with a +2 charge. We just talked about that. What about the chlorine? Well, we know that chlorine is in group 7A, and the chlorine can only gain 1, right? It won't do any good to the calcium to lose only 1. Then that's not going to do it, right? And chlorine cannot gain more than 1. So what ends up happening is that the calcium will grab 2 chlorine atoms, right? And the calcium will give this atom of chlorine 1 of its electrons, and this atom of chlorine 1 of its electrons. And that's perfect, right? Everyone is happy in this partnership, right? Calcium loses 2, each one of the chlorine gains 1. Beautiful, right? And then you have a compound that's formed of 1 calcium atom and 2 chlorine atom. And when we write the formula of this small compound, that would be Ca and then Cl2. The subscript here indicates that I'm using 2 of the chlorine atoms. Right? Okay, and that's a perfect, like I said, this is a perfect partnership. Okay, what do we name that? We're going to call that calcium. We start by naming the cation first, followed by the anion, which is chloride. I want to bring your attention to something here. And I see this every now and then, especially when we start learning about molecular compounds. Students, they do this mistake all the time. They start naming this calcium dichloride. This is a horrendous mistake, right? It hurts my heart when I hear that. Let me remind you with something important. The prefixes di, tri, and tetra, and so forth are only for molecular or covalent compounds. We never, ever use these prefixes with ionic compounds. Okay, so don't ever fall for that trap or forget. The prefixes di, tri, tetra, and so on and so forth, all of these prefixes are not for ionic compounds. They're only used when we name covalent compounds and molecular compounds in the next section in that chapter. Okay, so that is just called calcium chloride. Don't let that too confuse you. Okay, so I kind of showed you really in this example the concept, I wanted you first to get an understanding of how the bonding happens between 1 atom of calcium and 2 atoms of chlorine, and how the exchange or the transfer of electrons occurs. But there is a much different and a much easier way to write the formula of ionic compounds and also name them. Okay, we call this the crisscross method, and your book briefly explains the crisscross method, and that would be on page 57. Okay, I'm going to take one example from your book and show you that, and then I'll do a few more examples that aren't in the book. Okay, what is the ionic? Let's write the formula of the ionic compound that forms between aluminum and oxygen. And apologies about my handwriting here. Aluminum and oxygen. Okay, let's see what we know about each of these and how they'll combine. Well, first of all, aluminum is a metal and oxygen is a nonmetal, so they'll form an ionic bond. There'll be a transfer of electrons from the metal to the nonmetal. Okay, we know that aluminum is in group 3A, and it forms ion with a +3 charge, and then oxygen is in group 6A, and it forms ion with a -2 charge. Well, I can go and show you how I'm going to do it, like a step above or the process above, but I will just show you the crisscross method here because it's much easier. Okay, so the crisscross basically is that you're going to crisscross those charges that you see here as subscripts, right? So you're going to take that here and this here. And that's shown in your book. We're going to crisscross the charges into subscript. So the Al will get the 2 and the oxygen will get the 3. And the formula of the compound here would be Al2O3. Okay, and how do we name it? The name of the cation followed by the name of the anion. Aluminum, and the anion here is called oxide. So that is aluminum oxide. Now this crisscross technique is much easier because it avoids a lot of the thinking that you have to do on how these two elements combine. Remember that they combine so that the overall charge on the ionic compound is 0. Okay, let's look at a couple of other examples. Let's see. Let's do the example of magnesium and nitrogen. Once again, magnesium is a metal, nitrogen is a nonmetal. They form an ionic compound. Magnesium is in group 2A. It forms an ion with a +2. Nitrogen is in group 5A, right? And it forms an ion with a -3. And here we go, we crisscross charges. So once again, will be Mg3 and then N2. And what do we call that? Magnesium nitrate. Okay. Let's take a look at one more example. Look at the table here. Let's write the formula of the compound that forms between barium, which is a metal, and between, let's say, fluorine, which is a nonmetal. Let's write the formula and also the name. All right, barium is in group 2A, forms a 2+ charge. Fluorine is group 7A, forms a -1 charge. And then let's crisscross these, and there we go, BaF2. How do we call it? We name this compound barium fluoride. Okay, notice all the examples that I've used so far are examples of the main group elements. I've just given you examples from group 1A through 7A, right? But then we don't forget about those inner transition elements. But the same rules apply to the inner transition elements. What is the formula and the name of the compound that forms between iron, 2 ion, and oxygen? Okay, well, iron 2 ion, that would be iron with a +2 charge, and oxygen is a nonmetal, group 6A, and forms 2 negative charge. Very good. We can crisscross charges, and it would be Fe2O2. However, remember that we can reduce these into just 1-to-1 ratio. So remember that the idea here is that the iron is going to give 2 electrons, and the oxygen is willing to take both of these 2 electrons. So really, 1 atom of fluorine is going to give up 2 electrons. 1 atom of oxygen is going to give up 2 electrons, and they're going to combine together. So we don't write Fe2O2, we just write FeO, right? And we call that iron 2 oxide. All right, think about another way we can name this using perhaps the common naming that we just learned. What do we call that? Iron 2 is a ferrous, so we would call that ferrous oxide. Okay, I'm going to give you another example, but this time I'm going to flip things slightly around. So this time I'm going to give you the name, right? And we'll write the formula. Let's do cupric chloride. Okay, now you have a name and you're trying to write the formula. Same thing. Let's see, cupric. What is cupric? We know that cupric is a copper, and ic suffix indicates the higher charge, so it's a +2. Chloride is Cl with -1. Once you see these ions written down, then you can just crisscross the charges and it would be CuCl2, and that is cupric chloride. All right, I'm going to give you something else. Let's do something slightly different. How about if I give you this and ask you to name that? Okay, well, I could say iron chloride. Is that enough name? Is that an accurate name? No, it's not, because we know that iron could be a +2 or a +3. I have to indicate that in the naming. So the first thing is to figure out, is this an iron 2 ion or is it an iron 3 ion? And you already probably know it. Crisscross, we're going to do the same thing. I'm going to take that charge back, or that subscript right here back here, right? And there's a 1 there that goes there. So now we have an iron with a +2 charge. You know the chlorine's -1. Okay, that now we can name it. That is iron 2 chloride, or ferrous chloride. Okay, so all of the examples that we've had and we've looked at, all of these ions, these are called the monoatomic ions, right? They're ions formed of just one atom with a net charge, negative or positive. There's also ions that are polyatomic, ions that are formed of more than just one atom. They're a group of atoms together that carry a charge. So, for example, hydroxide ion is an oxygen and a hydrogen with a negative charge. It's a group of atoms. It's 2 atoms really, right, together, and then they carry a net charge. This is called hydroxide. Okay, sulfate is another example, and it has a -2 charge, a net charge of -2. Phosphate is another example. Carbonate is another one. There's so many different examples of polyatomic ions, and all of these polyatomic ions are listed in a table in the book. Let me find it. And that would be table 2.3 on page 60. Table 2.3 lists all the polyatomic ion. Actually, it lists both the monoatomic and the polyatomic ions as well. The polyatomic ions that are listed in the table are very common, and we find them in a lot of compounds. So as we continue learning, you will encounter these a lot. And that's why it's really important to memorize the polyatomic ions. All right, don't just count that you have the table. You will need to memorize these. And the best way to do it is to not just sit and recite them, but practice. Right? Practice how to write the formula of ionic compounds. And when you practice writing the formula of ionic compounds, you'll find yourself, repeating the formulas and then really getting it and memorizing it. I'm just doing a couple of examples on how to write formulas of ionic compounds with polyatomic ions. Let's say we would like to write the formula of a compound that forms between sodium and sulfate ion. Okay, so sodium is in group 1A. We know that the sodium forms a cation with a +1, and the sulfate is a polyatomic ion. Okay, so what is the sulfate? The sulfate ion has the formula SO4 with a -2 charge. So it's a polyatomic ion. It's a group of atoms together, and they all carry a -2 charge, net -2 charge. Okay, and then we're going to do whatever we did before, crisscross ions into subscripts, so that will be Na2SO4. Okay, one more thing that we want to express here, or want to show you. Let's take a look at another example where it is slightly different. Let's do, for example, calcium hydroxide. I'm giving you the name here. Okay, and let's write the formula. Calcium, that's the metal, right? And that is in group 2A. It's a 2+ charge. What about hydroxide? Well, it's a polyatomic ion, right? And I just showed you up there that hydroxide has a -1 charge, right? So we're going to crisscross ions. All right, so that would be calcium 1 and then OH2. Well, whenever you are crisscrossing charges into ions and you're using more than one, so if it's a 2 or more, you have to put this in parentheses, right? So it would have to be calcium and then parentheses OH2, Okay, and that is the correct way. So anytime you're writing a formula and you're using more than one of the polyatomic ion, you would have to put that in parentheses. Okay, I'll do one more example. Let's write the formula of the compound ferrous nitrate. Okay, let's see. Ferrous, that would be iron with a +2 charge. Nitrate is a polyatomic ion with the formula NO3 and a -1 charge. So we're going to crisscross charges. So that will be iron 1. We omit the number 1. And then the nitrate, I'm going to use 2 of them. So I have to put it in parentheses. That would be NO3 2. One last example, and I will leave you with this. Let's write the formula of ammonium sulfite. Ammonium sulfite. Ammonium. Ammonium is a polyatomic ion that has the formula NH4 and a +1 charge. Ammonium. Okay, need you to remember that because ammonium ion is different than ammonia. So it's important that you remember this. Ammonium ion is the only polyatomic ion that has a plus charge. That should help you remember it. Ammonium ion is the only polyatomic ion that carries a positive charge. All other polyatomic ions are negative, are anions. Okay, here's the ammonium, and then the sulfite is an SO3 with a -2 charge. Okay, all right, well, that makes it a little bit easy now. We can just crisscross charges. So I will take this over here and that over there. Okay, so the ammonium will get the subscript 2, and we know we have to include that in parentheses. So ammonium NH4 in parentheses with a 2 on the outside, and then an SO3. And that would be ammonium sulfite. Okay, this is the last example I have for you, and I hope this helps you. I know I was a bit fast, but the purpose is a review of all of the naming. All right, I will see you in the next video.